Okay, hi everyone. In this video, I'm going to work through heating curves. In the last video, we talked about phase changes and the directionality of the energy flow. And in this video, we are going to work to try to quantify that energy flow. So, the example that we're going to work through is that water is frozen using liquid nitrogen, which means that it has a temperature of 77 Kelvin or negative 196.15 degrees Celsius. This super cold ice is then placed in a container on a hot plate. The hot plate is turned on. What happens? Well, what happens is initially the temperature is going to increase. And this is the warming of the ice. And when the ice reaches 273 Kelvin, or 0 degrees Celsius, the freezing point of water, the ice is going to start melting. In this melting, heat is going to be added, but the temperature is not going to change. Eventually, all of the ice is melted, and then as we start adding heat, it is going to warm. This is water, liquid, is now warming. If we keep adding heat, eventually at 373 Kelvin or 100 degrees Celsius, that water is going to start to boil. And while that water is boiling, as we add heat, no temperature change happens. Eventually, if we are in a sealed container, we will have converted all of that liquid water to gaseous water, and then adding heat can again warm the gas. So this diagram is what is known as a phase diagram or a heating curve. And that is because we can indicate what phases we have at what points. And so this first portion is where we have ice. Once the temperature reaches the melting point of water, then in this region, we have ice and we have water, liquid. So water solid and water liquid. Once we have added this much heat and we have melted all of our ice, in this warming region, we only have liquid. And then eventually that liquid is going to start to boil. And while that liquid is boiling, we have liquid and gas in the mixture. And then after we have converted all of the liquid to gas, then we can go back and we can start warming again. And in this final region, the only thing that we have is gases. Okay, so another thing to know is that above gas, there really isn't another phase. Okay, so how now we can start to think about how to quantify the heat that is added. And so in the first part of this problem, we are warming our ice cube. And I didn't give you the mass of the ice cube. We are warming the ice cube from 77 Kelvin to the melting point, 273 Kelvin. And when this temperature is changing, so notice that in this graph, the temperature is changing. In these regions of the heating curve, when the temperature is changing, we solve these problems with calorimetry. And so that's the Q equals MC delta T. But, okay, so let's do an example. So how much energy is transferred when 14 grams of ice is warmed from 77 Kelvin to 273 Kelvin? And it gives me the specific heat of ice is 2.09 joules per gram degree Celsius. So we're looking for Q. My mass is 14.0 grams. My specific heat is 2.09 joules per gram degree Celsius. And my delta T is 273 Kelvin minus 77 Kelvin. Now, those of you who are astute probably notice that my units aren't going to cancel. And so what I'm going to do is I'm going to convert these to Celsius so that my units work. And so to do that, I'm going to subtract 273 from each. And so I have 0 degrees Celsius minus a negative 196 degrees Celsius. And so if I work this out, I get Q equals 5735 joules, or 5.735 kilojoules. Now, at a phase change, the heat is being added, but no temperature change occurs. And the heat that it must be added is based upon this delta H, this enthalpy of the phase transition. And so in these regions, there's no temperature change. And so the Q is going to be our moles involved times the delta H of that transition. Okay, so let's do an example. How much energy is transferred when 14 grams of ice is melted? The enthalpy of fusion for water is 6.02 kilojoules per mole. And so the Q is going to be, the first thing I have to have is moles. And so I have to convert from 14 grams. Water is 18 grams per 1 mole. And so 0.778 moles of water. And the delta H of fusion is 6.02 kilojoules per mole. And so the Q for the melting, this green region, the heat that is transferred, is going to be 4.68 kilojoules. Okay, so I recommend when you're solving these problems, always to draw your graph so that you are able to separate when you are heating something versus when you are going through a phase change, because the process of solving the problems is different whether you are doing phase changes, which is Q equals N times the delta H, or whenever you're warming, and that is calorimetry, Q equals MC delta T. Okay, so we're going to keep working with phase changes and energy, and I will see you in the next video.